everybody. So we will see how to solve one or more numerical on the stress strain diagram, right? Okay, fine. So here we are seeing that here are the different values which is given in the numerical problem. The diameter of the steel bar. Diameter of the steel bar means what? That if we are having our specimen like this, okay, this I've already told you that this is known as the gauge length. Gauge length, and the length and its value is 20 centimeter. Okay, and the dia of this gauge is 3 centimeter. Right. So it means what? That we can take the initial length, that is Li, as 20 centimeter and the Di as 3 centimeter. Okay, fine. Okay. What else next? The load at the elastic limit is 250 kilonewton. In that case, if we draw the stress strain diagram for it, if we draw the stress strain diagram for it, right? So it is saying that the load at the elastic limit. So this is the P, and suppose this is the E. So the load at this limit is 250 kilonewton, right? Okay, and the extension at a load of 150 is 0.21. Okay, now just mind it that it is saying the load at 150. It means what? That this load might be lower than the load at the elastic limit. It means that this load might be lying somewhere out in this point, right? Somewhere. Say, suppose this is the point. So this load, 150 kilonewton, is lying in the within the, we can say within the removed. If this load is removed, the specimen will revert back to its original configuration, right? Second thing, I'm sorry, Hooke's law is followed. Hooke's law, that is, the stress exactly is proportional to strain, is followed here. This is followed in this limit, right? So in that case, we can say that if we remove this load 150, then it will revert back to its original shape, right? Okay, fine. Now maximum load, it is saying that maximum load of 380. It means what? That this maximum load is where? Here, no, here, no, here, yes. This is the maximum load, 380 kilonewton. Means after that, there will be the initiation of necking region and leading to fracture. Fine. Next, total extension is 60 mm. Okay, fine. So we find out that the delta L total extension is your 60 mm, right? And the diameter of the rod at the failure is 2.25 centimeter. In that case, we can say that if this is your specimen and it has got break into the cup and cone structure like this, so this diagram, sorry, this diagram is not so good, nice, but still I hope that you can assume this dia out here, is 2.25 centimeter, right? Okay, means the final dia, right? So this is all about the stress strain diagram of this numerical and the diagram of the specimens, right? Now we will solve it out. Okay, fine. What it is asking, now we see that what it is asking for. Well, it is asking for the Young's modulus, right? Means E. We know that the E is what? Stress constant. We should not forget that it should be within the elastic limit. So it means what? that the stress cost must be, or not caused, man, we should write induced, the stress induced, okay, must be within the elastic limit. Fine. Okay, the stress induced must be within the elastic limit, and hence the strain should also be in the same limit. The strain should also be in the same limit. It will happen when the load, it will always happen when the load is applied, the load is applied within the elastic limit. Fine. So we say that we have inferred that if you have to find out the value of E, in that case everything should be within the elastic limit, everything, right? Okay, in that case we find out if E is equal to sigma upon strain or epsilon, then sigma is equal to P upon A. This is the load within the elastic limit, and what we see, is it 250? No. Is it a load of 150, which is lower than this, and this load is being applied at the elastic limit, so we have to take a load which is lower than that, right? In that case this will be equal to 150 upon A. We have seen that we have to calculate the engineering stress strain, and for that case the A should be your original cross-sectional area, the area of section, the area of cross section should be the initial one. Okay, fine. So this is your pi by 4 d square, or we can say d naught square. So 150 upon pi by 4 into what was the area? Sorry, dia. That is the 20 centimeters. The length of the was 3 centimeter. So it will be 3 square. You can change the unit as per your choice. This is centimeter. This is mm. This is mm. This is centimeter. So you have to mind it out because all the units should be the same, right? Generally we go for mm and meters, right? Okay, nice. So it is all about how to find out the Young's modulus of elasticity. Now we will find out that how will you find out the stress at the elastic limit. It's very easy, man. If you have to find out the stress at the elastic limit, is what? Load upon area. It means what? That the load should be also applied, it should also have been applied at elastic limit, and this area obvious, it will be the same, that is the original area of cross section. Okay, fine. So we see that what is the load applied at the elastic limit? It is your 250. So it will become 250 upon into 10 to the power 3 upon the original area of cross section, that is pi by 4 into d square. So 3 square, 3 you can change into meter, right? So it can become 3 upon 100, right? Square. Done? Okay, fine. Now we find out what is the percentage elongation. What is the percentage elongation? So we see that the total elongation that has taken place is 60 mm, right one, upon what was the length at the beginning, that was 20 centimeter, right? It is in m. So we can find it out simply 20 into, you can do it by 20 upon 100, right, into, to get it change into mm, right? 20 centimeter. Should we change this or this? Whatever you change, you have to take the ratio, right, into 100, right? You will find out the elongation. Okay. Okay. Second thing is there. What is the percentage decrease in the area? Means A initial minus A final upon A initial into 100. Why we are taking like this? Because A initial is more than A final. And the A initial is the pi by 4 into D initial square, and D initial is the diameter of that gauge, that is your steel bar 3 centimeter, right? And if I say AF, that is the diameter after the specimen has got filled, and that specimen has got filled at which diameter means what is the dia of the rod of the failure, that is 2.25 centimeter. In that case this will be pi by 4 into 2.25. if you want to change into centimeter, meter, whatever it's your choice, right. So centimeter or the meter, whatever be your choice. So that is 10 to square, right, 100 into meter, right. Okay. So this is all about how we do find out the elongation, the decrease, and the stress, and the Young's modulus. That's all for now. Thank you very much.